So this is going to be a short video to describe or to summarize uh, the effort to integrate AWP or kernel calculations based upon the forward simulation code AWP into my full 3D waveform inversion code, the F3DWI code. So the current status of integrating these two sets of code is pretty much complete up to the point of kernel calculation. So kernel post-processing has not been uh, modified yet, right? But so KPP, the binary KPP hasn't been actually updated to deal with the AWP kernels yet. Um, but I suspect there's not much to be done there because um, the output format for kernel calculations for AWP is actually identical to the one for SW4, right? So if the kernel post-processing code works for SW4, it should work for the same output generated by AWP. Um, so I haven't actually validated that yet, but that's gonna be my expectations. So here I'm still working. I'm using the half space example as an example to discuss how to use the updated set of code to run AWP, and then using the output of the AWP to compute volume kernels, right? Volume data sensitive kernels, 3D volume kernels. So here I'm inside of this particular directory on Teton, right? That's the UW's cluster, and there are a few files that's kind of necessary to initiate the entire workflow. So that's the parameter file, basically the control file, and the control file has to follow a certain kind of format. So if um, I sort of discussed this kind of format in previous videos, but now there's more keyword value pairs, right? Um, so that's gonna be where my binaries are stored. So uh, So that's all the binaries that's needed in order to actually carry out all the calculations that I've discussed in my previous videos and also in this particular video. Um, so that's the bin directory, right? That's the bin directory. And if you try to actually compile it using CMake, the procedure is relatively straightforward. It involves some kind of tweaking, maybe, right? If the setup environment is slightly different, but in general, it's relatively straightforward. And so you may have noticed there's one more binary called AWP here, right? That's the AWP binary, and this AWP binary was created by using another CMake file that I just created. Um, so there's one more CMake file that's needed in order to actually compile the binary AWP, right? And uh, depends upon the compiler. If it's a GNU Fortran, then I need to add this particular option to the compiler flag. And if it's a Intel Fortran, I need to add this particular flag to the option, right? And and then the executable AWP depends upon all those .f, those Fortran files, and then the installation directory is going to be uh, underneath the bin of the top level F3DWI directory, and then the rest of the rest of the the rest of the binaries are some stuff that we have talked about in previous videos, but now they have different kinds of command line inputs and different kinds of capabilities. Uh, and then this line is pretty much useless now. So there's no Python scripts anymore. But this line is still useful. Work dir, job dir, right? You have to specify the work dir, job dir, and then the directory where you want to the location where you want to store the XYZ GRD file. This is actually a mesh file that's going to be used uh, for the kernel related calculations. And then UTM zone. So here it's basically just a bunch of key value pairs that's used for creating the box for doing the AWP wave propagation simulations. You have to specify the zone, right? UTM zone. The first point, longitude, latitude. That's the lower left corner point. That's the P1. And then P2 is the upper left corner of the box. And then X max is basically the direction, the x-axis, right? So from point 1 to point 2, that's a y direction actually. So by specifying these 2 points, you pretty much have the dimension of the y direction. And then you also need the x dimension. The x dimension is the size of the box in from point 1 to point 4 actually, right? So if it's a clockwise 1 2 3 1 2 3 4, right? That's the x dimension. And then z max, that's the depth dimension. And then grid spacing is like 100, and then how many processes we are going to use for the calculations in the x, y, and z directions. So this calculation is going to use 64 CPU cores in total, right? And then where the velocity model is going to be stored, the minimum and maximum velocity, minimum shear velocity, maximum p velocity, right? Source receiver list, where the source and receiver. This is another file that has to be created by hand. The total number of the total duration of the simulation, that's like 15 seconds. I want to compute the synthetic seismograms for like 15 seconds, and then the time interval for the simulation, time step interval for the simulation. You have to the DT has to be small enough to warrant a CFL condition is met, the stability condition is going to be met, and then a bunch of things that's going to be needed by AWP. So VSCO is like attenuation coefficient. Do we want to account for attenuation in the simulation? And then source tensor size 1, 1, 2. These parameters are used for source inversions. And then NX skip, NY skip, and NZ skip, that's the uniform decimation rate for storing the strand fields, right? And NT skip. That's the decimation rate in time axis. And then these 2 lines are kind of new. I par flag equals to 2, which means we want to compute the kernels for VP, VS, and density, right? And then that's like 3 parameters, right? 3 model parameters. And then IK flag 110 means I want the kernel for VP. I want the kernel for VS, but I don't want the kernel for density. That's like 2 lines of two new lines of parameters, right? And then if you want to look at the second file that's needed in order to actually initiate the entire calculation, is srinfo srlst. That's this file, right? The format is pretty much the same as before, so I have explained the format of this particular file in previous videos, and the only thing that I have to pay attention to is the source time function for the Green's functions. So these .x, .y, .z are these 2 directories, or these 2 sources are actually in pointing pulses for sources located at the receive location in.rc01. And then the source time function that's used for computing the Green's functions are this impulse. It's basically just a Butterworth low-pass filter with fourth order Butterworth low-pass filter with corners at 3.5 Hertz, and the time sampling rate for the source time function is 0.015 seconds. And the format, so this is like a source file that I have to edit by hand, right? And this file can be created by using MATLAB or any kind of a program that can actually create this kind of an impulse, right? And then it's got a specific format, right? And if I just want to look at it, the first 3 numbers, the total number of points, the beginning time, and then the time sampling interval, right? So that's and then the total number of lines in the file is going to be 501 plus 1, 2, 3, the 3 header lines. That's sort of the format that's needed by for describing the source time function. Yeah, that's pretty much everything that's needed in order to actually start to bootstrap the entire process for computing the kernels, right? So and then the entry level code is called box. And then if you are actually giving it just a one input parameter, say parameter hs.dat, it's going to try to actually look for, it's going to recognize the different formats of the parameter control file, right? The control parameter file. If the format is like something equals to something, this kind of with the equal sign, then it's going to, by default, it's going to recognize it as a SW4, AWP input. But if it's a colon separating the key value pairs, then it's going to recognize it as SW4 parameter input. So if you just give it like one input command line arguments, then it's going to search for all the required key value pairs inside of this particular control file. And then it's going to generate two outputs. One is going to be the box.dat, that file that just created, right? And then inside of this box.dat file is going to be the longitude and latitude of the four corners of the simulation box. And then a second output is going to be the XYZ file. That's inside of the velocity model. That's inside of the velocity model. That's this particular file, right? Both files are generated by the box binary, right? And this file is particularly important because it stores the mesh information. It's a uniform mesh, but nevertheless you still need the mesh information in order to actually do the rest of the calculations. So that's the two outputs generated by box, right? The binary called box. So how does box actually know where to put this XYZ GRD file, right? Because inside the parameter control file, the control parameter file, you specified it. So it's going to create the XYZ GRD file exactly at this particular path, right? And it's going to complain if this path doesn't exist, right? And then that's the first file inside of the VM directory. That's the velocity model directory, right? And then the second thing that we want to do is to actually create the velocity model. And for AWP, it's different from SW4. SW4 just creates like a one file, the .r file, that has a specific R file format for storing the velocity model together with topography if there is a topography. AWP is different. It's gonna require a velocity model for each chunk or each partition in X, Y, Z and dimension. So in this case, you're gonna need, if we have like a 4x4x4, this many 64 4x4x4, right? That's 64 processes. Then we are gonna need like 64 files for storing the velocity model, and each file is going to be used for storing the velocity model for just that partition of the spatial domain. And then how do we actually do that, right? We can f3dwi bin. We can use the same binary called rg. And then we still need to give it the parameter control file. And then if we just want a half space model, suppose we just want a half space model with p velocity equal to 65,000 meter per second, right? No, 6,500. I think. I can't remember. Let me see. RFG. No, RFG, right? Okay, 6,500, right? So RFG, right? And then parameter 6,500. That's VP, right? And then VS 3,500, and then density 3,000, right? That's gonna create a velocity model for a uniform half space with the VP, VS, and density given by these three values, right? And then the code is going to automatically partition the velocity model for each of the processes, and then it's going to create a bunch of files that's called HSGRD, this thing, and followed by the 9-digit partition ID, right? Um, how does it know to actually create this kind of file format and in this particular directory, right? Again, it's inside of the parameter file. You have specified where the media directory is going to be and what's going to be the prefix, right? Uh, so it's just going to do this. It's just going to read this particular line and then append the partition ID with the 9-digit partition ID behind this particular prefix. Right. Again, it's going to complain if the path doesn't exist. Right. That's the second set of files inside of the velocity model directory. Right. And then that's the velocity model. This velocity model is going to be read by AWP. AWP is going to read this velocity model, and then it's going to do the wave propagation simulations. In the past, this particular file was created just in 4-byte floats. So these are all binary files. In the past, it was 4 bytes, right? 4-byte floats. So every grid pointer is going to store VP, VS, and density as 4-byte floats, right? 3 floats. But now it has been changed to doubles, right? I have changed that to doubles and changed AWP to read those double binaries. Right, so the size of those files are going to be like twice before, right? Um, um, so that's the second set of files, right? Second set of files in the VM directory. The third set of files is going to be the uniform recording grid for storing the strand views, and this file has those files has to be created by using URG, uniform recording grid. And then the URG code only requires like 1 command line input. That's a parameter file. And then if you run it, it's going to create a bunch of files that's going to look like HSGRD with REC and then followed by the 9-digit partition ID. And these files are just text files, ordinary text files. And then if you want to look at one of them, it's going to look like that. So this file is going to have like 900 recording grids, and these are the coordinates of those grids. And then it's 15 in the x direction, 15 grid points in the x direction, 5 grid points in the y direction, and 12 grid points in the z direction. And then the recording grids are going to be organized in the z slowest, x fastest fashion, right? And then because the decimation rate is specified inside of the parameter file, right? The decimation rate is going to be 888, right? It's going to be 8 in x, y, and z direction. So the first index is going to be 1. The next index is going to be 9 in the x direction, right? And then 9 plus 8, that's 17. So the skip rate is like the decimation rate is like 8, right? And then x is the fast direction, z is the slow direction. One of the things that I have to remember is that those recording grid coordinates are actually local grid recording grid coordinates. So AWP actually requires these grid coordinates to be local to each of the partition. It's not the global recording grid, global grid ID, right? So if you look at some of the, say, the last partition 30303, right? So it's pretty much the same, right? 1917, right? This is one of the most important differences between AWP and SW4. SW4 actually requires what? SW4 actually requires the recording grid ID or coordinates to be global. It's not specific to each of the partition. It has to be global. Right. 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 This is the last partition, right? But if you look at the first partition, Um, and then another difference is that you don't see the 3 integers describing the total number of grid points in each of the direction for that particular partition in the SW4 file, recording grid file, right? And then a third difference is the first column. The first column is actually the grid ID because SW4 uses a composite grid, right? You have multiple grids. You have so you have a grid ID, right? But SW4 has just like one grid, so there's no. The first column is not really the grid ID. So that's some of the very important differences between SW4 and AWP. So that's URG, right? That's URG. And then there's one more thing. That's RRG, random recording grid. The random recording grid is needed in order to actually extract synthetic seismograms. For SW4, the synthetic seismograms are automatically computed because you have to specify the receive locations at inside of the input file for the SW4, but AWP doesn't. AWP doesn't have to actually create synthetic seismograms. So what you have to do is to actually put a random recording grid at the location of the receivers. So in order to do that, what we have to do is to use the binary called RRG, and then again reads only just one command line inputs, and then that's gonna generate the last set of files inside of the velocity model directory. Alright. That's these files. Most of those files are actually empty. Not exactly empty, but has a number 0 inside of it, saying that there's no recording grid in that particular partition. But if for a file that has recording grid, the format is actually quite similar to the uniform recording grid. Right, so it's saying that I've got like 45 recording grid inside of this particular partition, and then that's the coordinates or local coordinates of those recording grid in that particular partition. Right. So that's pretty much all the files that's needed in order inside of the VM directory. Right. One important difference between the velocity model files in AWP and SW4 is that the velocity model files are partition dependent, right? So every partition has its own velocity model file, and this velocity model file is not decimated in any way. It's this velocity model file actually describes the velocity at every grid point for the finite difference simulation, right? There's no decimation. But inside of the SW4 VM directory, the actual velocity model used for finite difference simulations are actually given inside of the R file, right? This because it's a half space, right? So there's no R file. It's just given by the keyword. So SW4 right. So that's the line of code for specifying a uniform half space model with a fixed value of P and VPVS and density, right? So yeah, that's the velocity model that's used by the simulations. And then those model files were used actually when during the kernel calculations. And those model files has to be created by setting the write info flag to 2, and then run the SW4 simulation code. Then it's going to generate those decimated model parameter velocity model files, right? On the decimated recording grid, and those files are going to be used by kernel calculation code later on. Again, those files are binary, double binaries. You don't even have to actually read them, right? Those files are created automatically, but they are going to be needed during the kernel calculation stage later on, right? So that's another very important difference between AWP and SW4. So for AWP, those velocity model files are used by AWP final difference simulation, and they are not decimated. Those files were inside of SW4. Those files uh, were not used by kernel calculation. Were used by kernel calculation. They are not used for the final difference simulations. Um, Okay, so that's pretty much all the files that's needed in order to inside of the velocity model directory. And then the next step is going to be creating the right directories, creating the right directory structures for the AWP wave propagation simulations. And then the procedure for doing that is um, is um, is relatively straightforward. So uh, the first thing we have to do is to actually write the point source input file inside of each directory. That's by using uh, that's by using a binary called WPS, right? Called write point source. So Bing write point source, right? So this write point source file is going to read the SR list source receiver list file and then create the source input file and then generating the correct directory structure. Uh, and then this particular binary is going to require let me see. It's just going to require the input file and then the starting and ending line number inside of the source receiver list. So if I open the source receiver list file, uh, it's got like it's got 7 lines in total, right? Uh, so every line that starts with the index 0 with number 0 is actually a receiver line. It's not a source line, right? So WPS knows to skip those lines because those lines are not exactly actual sources, right? And then the actual earthquake sources are gonna start with the flag 1, and then the Green's tensor sources are gonna be starting with the flag 2, right? So WPS actually knows how to actually read those flags and then try to create the correct output format. Uh, and then all we have to do is to actually specify the range of the sources that we want to sort of create the directories for, to create the sources for, right? And then the output of this code is actually inside of the FWF directory. If the FWF forward wavefield directory doesn't exist, this code is going to create it. It's going to create this directory by default. And then the output file is going to be this file, right? So if you don't believe me, let me just do an LT. Then that's the output file, right? So if you want to sort of look at the format of this file, you don't really have to actually look at the file at all, because these files are actually, it's an ASCII file, right? But it's going to be a file that's going to be read by AWP, right? So it's an explosive source. So you only see like the first 3 columns. That's MXX, MYY, and MZZ. That's the diagonal of the moment tensor. So, and then the first row is actually the grid location of the point source, and that's the source type. And then the source time function, it's gonna actually use the correct source time function for as specified inside of the source receiver list file. So if you want to source time function is gonna be, for this particular source, it's gonna be this thing, right? That's like a Gaussian. This is actually a Gaussian file, I think, a Gaussian thing. So it's got a 101 points. Beginning time is 0, and then the time sampling interval is like a 0.02, right? And then for this particular source, it's gonna use this the same source time function file. And then for this particular Green's tensor source, it's gonna use this low pass filter, the Butterworth filter as the source, and then do that, and then create those files, right? Um, and that's pretty much it. That's pretty much it. But there's one more step before you actually run AWP. That's called pre. Uh, the purpose of the pre is to actually create. There's another input file. That's the control parameter file that's needed in order for AWP to run. So if you look into FWF 1001, right? There's one more input file, in3d, right? WPS is going to create this source file, input file, and then you're going to need this thing, and then you're going to need a soft link to the AWP binary in order to actually run the code, right? So pre is to creating this in3d input file, and then this soft link. That's this file is kind of it's not difficult to create this particular file because the content of this particular file is pretty much just a duplicate of the parameter control file with some kind of directory structure inside of it, and then also specifying the source input file, that kind of thing, right? So that's gonna be how this in3d file is gonna be. So all I have to do is to call pre, right, and then parameter file 1 to 7, right? Then that's gonna automatically. So it's saying error creating the soft link because that link is already there, right? Already exists. But it looks like I had one more slash here. It's in the start of the error message. Let me look at my pre-code. Okay. SRDRR. Okay, so SRDR is what? SRDR. SRDR has a backslash inside of it already, so I do have to sort of get rid of this backslash now, right? Right. I'll register this change into GitLab later on. So, but this error message doesn't really matter. It just says that the soft link is already there because I had done this run before, right? And then if you go into one of the source directories, you're gonna see a job script, and this job script was not created by the software. You have to actually create it. And if you have lots of sources, it might be easier to actually write a script to create those job scripts inside of each of the event directory. Right? It's not so difficult, and it depends upon the job management system on your cluster. So the only thing that's kind of useful is this line of code that's gonna call AWP, right? And then on Mount Moran, all I have to do is to do not Mount Moran, on Teton, all I have to do is to SBatch run.sh, and then it's gonna run. And then after it finishes running, it's gonna create all the stream views inside of the output VOM, this particular directory, and it's gonna be named like SX96PV stuff, right? And then that's for kernel calculation, the stream views in the uniform recording grid. And then these files are for source receiver for synthetic sidegrams because they are at the random recording grid points. And then once we want to sort of extract the synthetic sidegrams, we will need to read those binary outputs. Right? All those outputs are actually binary. So that's the source, right? And then if you go to the Greenstanzer directory, so for the half-space experiment, we are using the x direction, the x direction of the receiver as the source, right? You're gonna see pretty much the same thing, right? So the job script is pretty much the same, except that the job name has been changed from like a 1001 or 10001 to this job name, and everything else is like identical. And this can be easily achieved by writing a Python script or something, right? Uh, so for this particular exercise, it took like just 2 minutes to actually finish the run. It's not a huge run. Um, and then and then once the calculations are once the final difference simulations are done, there are a few things that we need to do. One is to actually extract the synthetic seismograms. And the way for doing that is by uh, using F2S, using this binary, F2S, right? So again, this F2S is going to read the random recording, the strand fields at the random recording grid points, those files, and then find the location of the receiver, right? And then just read the strand fields and together with the velocity fields, right? And then it's going to create, because it's synthetic seismogram that's going to be used for making misfit measurements, so it's only going to write out the velocity at the receiver locations. So it's not going to write out the strand fields. So if we, in order to actually extract the synthetic, you have to sort of specify the source and receiver ID. So 2211, that's like the index of the source and the index of the receiver, right? Why you have like 2211? Why does it repeat, right? Because it's expecting a range. So 22 just means it's line 2. That's this particular source, right? And then 22, we have like two sources here, right? Two earthquakes here, right? If it's 23, then it's gonna do extract a synthetic seismograms for these two sources, and then these two numbers are for the receiver range. 11. This is the receiver, right? But suppose we have multiple receivers, right? You have to then specify all the ranges, the line range. Suppose you have one receiver here and then another receiver here, right? So it's 17 if you want to include both sources, right? It's gonna skip all the source, the actual earthquake sources or impulse sources by looking at the first flag, right? Um, so so F2S, right, and then parameter file 2211, and then it's gonna generate the synthetic seismogram and then put it into this particular file, right? It's gonna be named as it's going to be located inside of the forward simulation directory, and then it's going to named after the receiver ID with a .txt appended, right? So it's going to be a ASCII file, right? And then the first column is going to be the time axis, right? And then the next three columns are going to be the velocity in the x, y, and z direction. That's the box direction, right? Box coordinates. If we want a east and north direction, and then the radial and transverse direction, that kind of thing, that can be appended later on to the as more columns, right? But for now, it doesn't have it. It only has the x, y, and z direction. Maybe it's useful to actually create the r and t direction also, but I haven't done that yet. So that's the synthetic seismograms, right? And then in principle, the next thing is to actually make the misfit measurement. The next step is actually making the misfit measurements, and then record the process of making misfit measurements into a particular file called the window file, right? And then the window file I have created. The window file is just called. It's following the synthetic file name with .win as appended. So we've got like three windows. All of them are measured on the zeros component. Zeros component is the x component, right? The first column is time. So the actual velocity actually starts from the second column, right? And then that's the x component. If it's x component, then the first column is zero. That's the channel ID. -1 means it's cross correlation. It's broadband cross correlation. Broadband cross correlation delay time is misfit measurements measured on displacement. right? Um, and then the WPK calculation is expecting velocity as input, velocity seismogram, synthetic seismogram as input, but the measurement was made on displacement seismogram. So this is like a subtle difference, but it's kind of important. And then the window has like 4 parameters because it's a tapered window, right? So we've got like 3 windows. The 3 windows are centered around um, the direct arriving P, surface reflected P, and surface converted PS, right? And one thing that I has to pay attention to is that the location of the window has to be after the actual synthetic velocity convolved with the source time function used for computing the Green's functions. Um, it's not before, it's after, right? So when you actually pick the time windows, you have to sort of convolve the actual synthetic seismogram that's extracted from the AWP simulations of the actual earthquake with convolve it with the source time function used for computing the Green's tensors, and then pick the windows based upon the waveforms or synthetic seismograms post convolution, right? That's one of the things that's kind of important, right? Um, because the source time function used for computing the Green's tensor could have a time shift, right? If you are using a zero phase source time function for the impulse, then you don't have to do this kind of thing, right? But it's kind of rare to use a zero phase source time function because that's going to give you a non-zero amplitude at time zero, right? That's not something that's not common. So once this particular window file is created, the next step is to create the WPK file, right? Um, and then in order to do that, we have to call WPK, right? It's going to require the parameter input, and then it's going to require a text file called wing list, and this wing list can be easily generated by wing list. For now, we have just like a one window file, right? So you can just do an AOS /AOS and give the complete path to the FWF, right? And then star, right? And then star.wing, right? That's gonna give you all the window files inside of your forward simulation, forward wave field directories, and then put those files into like a text file, and then feed it to WPK, right? Um, and then do I have it? Yeah. Right. And then the last input is going to be the source time function that's going to be needed in order to for the source time function used for the for computing the Green tensors, right? And then it's going to create a WPK file for each of the window file, right? So if you look into the you're going to see a new file, right? But the convention is kind of different from the .wing convention, right? This .wing file is going to be one file for all the different components inside of the synthetic seismogram file. But the WPK file is going to be different. It's going to be one file for each component, right? So here it's a component ID. The reason is because measurements made on different components will require Green's tensors, different Green's tensors, right? Will require different Green's tensors. So you need to record the component for each of the WPK because that's going to be the source time function, or that's going to be needed in order to actually compute the kernels for that particular component, right? So that's one of the things that's kind of different from my previous videos. So you need to actually keep track of the components when you actually create the WPK output files. And again, the WPK output files are kind of ASCII files. So let me just look at a few lines of FWF. Right. Most of them are actually zeros, right? But at the location where the time windows are, it's going to give you non-zeros. And then the first two rows are actually the starting and ending index of the non-zero numbers. inside of this particular file. So, and this WPK has to be used by the kernel code, right? And then in order to actually start the kernel code, you have to sort of create another file called WPK list, right? And it can be easily created, but the important thing is that you have to create the correct directory structure for storing the kernels, right? And if you look at my directory structure, it's inside of this KER directory, and then inside of the KER directory, you have to sort of organize it according to the source first, right? And then the receiver, right? That's the correct directory structure. And then you have to actually create a soft link to that particular WPK, to every WPK, right? And then when you create the WPK list file, you have to do the again complete path to the kernel directory, right? KER start star, right? And then start.wpk. That's gonna give you the path to the soft link of the WPK. That's again how do you actually create this particular directory structure, right? So by now I'm doing that using a Python script, but later on I could actually integrate it into like the C++ code. It's not too difficult to do that, right? Um, and then that's gonna be the WPK list, right? So if I do a WPK LST, that's the content of this file, and this file is gonna be needed by DSK, the data sensitivity kernel code, right? So in order to run the data sensitivity DSK code, to compute the volume the data sensitivity kernels, that's the binary, and it's a pair binary, and then the parameter file, the complete path to the parameter file, and then the WPK list. One means I only want the volume kernel. I don't want the surface kernels. And then I can just submit this job. It's gonna create all the KV followed by the partition ID. Right? So each partition is gonna create a separate file for the kernels inside its partition. And then in order to actually make a plot of this code, I have to actually assemble all those different partitions into like one file, right? And the correct way for doing that is by calling called assemble grid partition AGP, right? And this is a new code, right? And then the parameter as the input, right? So then you have to sort of give it the prefix of the kernel, right? So without the partition ID, it's gonna look for all the different partitions by itself, based upon the parameter value. And then the next input is gonna be how many different types of kernels on each of the recording grid, right? Why it's 6, right? Because we have like 3 windows. We have three different measurements, 3 different windows on the X component, right? And then I'm actually computing what? I'm actually computing VPVS and VPVS kernel, right? VP and VS kernel. So that's 2 times 6, 2 times 3. That's gonna give you 6, right? And then the last input is gonna be 1, which means that I want to concatenate all the different subgrids. For SW4, that's understandable, but for AWP, we have just one grid, so there's no concatenation. But nevertheless, if we want to just a simple to manipulate the output grid, that's gonna be the concatenation flag has to be set to true. Okay, so I did something wrong, I think. Oh, I forgot to specify the output file. So the output file is gonna be 1. I forgot. The output file is gonna be dump, right? And then 1. Oh, sorry. Right. And then it's gonna create like 2 files inside of the directory that you specified. These 2 files, dump and dump.info. dump.info is actually a text file that can be looked at. So it's got 6 kernels, and then x, y, and z directions for each of the dimensions. So it's going to be a multi-dimensional matrix, right? The dimensions are from slow to fast, right? So the topmost row is like the slowest dimension. It has like 6, and then x, y, and z basically, right? 60, 19, and 45. X, Y, and Z. Um, and this is actually a binary file, right? The dump file itself is actually a binary file. The size of it is supposed to be multiplying these dimensions together, multiply with 8 bytes, so it's double, right? It's a double binary, and this double binary can be read into MATLAB to actually make the plots. So here it's how it's written, how it's read. So open this dump file, right? Read it, close the dump file, and then reshape it. So MATLAB has this convention. The dimensions has to be from fast to slow. It's not from slow to fast. So it's 660. So it's 45, 19, 64, 60, and 6, right? So you have to sort of put those numbers in there in the reverse order instead of from top to bottom, right? And then you can just make plots of it. So the source receiver plane is on the 11th grid point in the y direction. I have to squeeze it because otherwise it's not going to recognize it as a two-dimensional matrix. That's going to give you all the kernels. Right, that's all the kernels. Uh, so that's pretty much the entire workflow for computing all the kernels, right? One of the things that I have to remember is if I want to redo the same calculation multiple times, I have to remember to actually clean up everything. So if I look at the forward waveform directory, so for now I have a bunch of files inside of the output VLM, those binary files, right? It's not gonna overwrite. If I run this same simulation a second time, it's not gonna overwrite the entire file. It's gonna just overwrite a portion of the file, unless the output file, the new output file, is bigger than the old one, right? But if it's smaller than the old one, then it's not gonna destroy the old file. It's just gonna overwrite the first small portion of that big output file. So I have to actually manually remove all those old files by hand, right? It's not too difficult to do if the output files is not like too many, right? But if there's lots of the sources, like hundreds of them, those output files could be like tens of thousands. If that's the case, probably I will need to write a script to actually uh, to delete all those old files, right? Why is that? I don't really understand. It's probably just because one of the I/O flags inside of the AWP was set in that particular way, right? This is different from SW4. So that's one of the things that I have to remember. And aside from that, this is the current state of integrating AWP with SW4 into a unified inversion code, kernel calculation code, right?